Okay, so like last time we basically did the energy thing, and so like after this now we have this thing where we relate stress with the strain. So basically we know that the stress tensor and the strain tensor are basically both tensors. So like to relate both of them linearly is basically Hooke's law. So like Hooke's law states that there is a linear relationship between the stress tensor and the strain tensor. But like unfortunately to relate a tensor with a tensor with linearly, we need a fourth order tensor. Like as we did for vectors, to relate one vector v with u, we basically applied v is equals to au type of where a was a second order tensor. So basically to map to second order tensors, we need a fourth order tensor. And like a fourth order tensor has a lot of components which is I, j, k, and l. To like fully describe it, we need 81 coefficients, and like this is basically the generalized Hooke's law where like we have to find the 81 coefficients. But unfortunately this is not plausible. So like basically we obviously have some assumptions. So like now that we know that basically both stress and the strains are symmetric tensors, like symmetric matrices. So basically what we did is like we convert the sigma 1 1, like I mean since we will have a 9 by 9 matrix, sigma 1 1, sigma 2 2, sigma 3 3, and like all the other components. So basically what we did is we basically go in the line sigma 1 1, sigma 2 2, sigma 3 3, and sigma 4 4, sigma 2 3, sigma 1 3, and sigma 1 2. So like basically we basically construct the 2D tensor into a 6 cross 1 vector. And since similarly for the strain too, so basically since both of them are symmetric, we can basically convert the 9 entries into 6 entries, and like we consider them in the vector notation. This vector notation is called Voigt notation. So like basically now this is 6 and this is 6, so like basically this is a 6 cross 6 matrix with 36 coefficients. So like from 81 coefficients, we are now down to 36 coefficients which we have to determine. Still 36 coefficients is a bit on the larger side. And like basically what we can do is basically we can like write the cij, and so like basically we can write sigma I is equal to cij epsilon j. And we also know that this d phi, where phi is the energy density, so like we know that v phi is equal to d sigma times d epsilon, so like we can write it as sigma times d epsilon I. And basically what we can write is in this manner, that sigma I times is equal to del phi by del epsilon I, and we know that sigma I is basically Cij epsilon j. And like obviously from this tensor notation we know that it's basically a sum of Cij epsilon j. So like now what I can do is basically I can differentiate this with respect to del epsilon j. So like epsilon j would get cancelled and I'll get Cij here, and this would be equal to del square by del epsilon I del epsilon j. So basically what we observe that since Cij is equal to like del epsilon I upon del epsilon j are both equal, so like Cij would be equal to Cji, and there would be like a major symmetry. So like now from 36 components we have this symmetry in the c matrix. So that would now mean that we now only have 21 components. So like c12 is equal to c21, c13 is equal to this. So basically these are both. So like basically we only have to determine the upper half triangle of this matrix. So like now we only have 21 components. Like this is exactly what we did in the last video. So now further what we can do is simplify from this 21 components by considering it as an isotropic. Isotropic implying that basically for any in whatever direction I choose, basically the stress and the strain relations would be the same. So basically, no matter what I choose, so like epsilon 1 1 would be related to sigma 1 1 in the same way. So basically, what I did is C11, I wrote this C12 as lambda, and I wrote C11 minus C12 as 2 mu. So what I did is like I basically simplified this with respect to this. So like now I have the all the diagonal elements are sigma plus 2 mu, and all this 2 mu 2 mu 2 mu, and all this one as lambda, and rest of all the elements I basically wrote as 0, because since it's an isentropic, like it does not depend on the direction. So like all these components would be zero. Like I mean, then which would imply that sigma 1 1 would only go with epsilon 1 1, and so on for the rest of them too, basically. So I can write this as sigma 1 1 is equals to lambda times epsilon 1 plus epsilon 2 2 plus epsilon 3 3. And this is basically set 4 times epsilon 1 1, like 2 mu times epsilon 1 1. And so basically this is like the trace of epsilon, right? So what we can go ahead and write is, yeah, what we can go ahead and write is that lambda is equals to sigma is equals to lambda times trace of epsilon times the I vector plus 2 mu times epsilon vector. So basically what we have is now a single linear relationship between the stress vector times the strain vector. So like basically what we can do is now we can convert this is like basically writing sigma in terms of epsilon, right? So basically what we can do is we can also write epsilon in terms of lambda by just basically relating the trace of epsilon and lambda. So like this is epsilon and sigma. So like this is epsilon written in terms of the stress tensor sigma. So like after this, now that we have this, we can basically now find each and every stress strain components for this. So like this is a new uniaxial axial texture. So in this case, we have this sigma is equals to this sigma tensor. So like after derivation, like after putting this sigma into all this, so basically there is this derivation in the notes, but I'll just kind of tell you the final result. And basically the final result for like two or three cases are as follows. Like here is the summary. So like these are the Lamy constants which we basically initially derive, and like in matrix form we have these two equations which we wrote, like sigma in terms of epsilon and epsilon in terms of sigma. And like since now for the case of uniaxial stress, we can basically define this, like we have this sigma is equal to only one column and rest all of them are zero. We can basically define a sigma upon epsilon 1 1 as E, where E is equal to Young modulus, like obviously as we defined it. So basically E is a Young modulus, like obviously since we defined it this way, and E is the Young modulus and it's related with lambda and mu as this, like this. And we can also define the Poisson's ratio, like the Poisson's ratio is equals to V, and we can define this in terms of lambda upon 2 upon lambda plus mu, which is equals to epsilon 2 2 upon epsilon 1. So basically, this is basically how we define Poisson's ratio and like the Young's modulus, and we are just basically relating this Young's modulus and Poisson ratio with this lambda and mu parameters which we initially derived. So basically, we can also write lambda and mu in terms of these two, Poisson's ratio and Young's modulus. So basically, depending on your choice, you can basically select lambda or mu, or you can basically select epsilon, like the Young's modulus and or this. So basically, in terms of Young's modulus and this Poisson's ratio, the epsilon and sigma relationships can be written as in this way: 1 plus V by epsilon sigma times V by E Ts of sigma. And like in the last case that we have is hydrostatic compression. So like in hydrostatic compression, our sigma is basically of the type minus P times I. And like so like it's basically like pressure is being applied from every side. So basically putting this equation in the last one, we get epsilon is equal to 2V minus 1 by E and P times delta Ij. So like basically epsilon also we only have this like axial strain. We do not have shear stress for this since it's a delta Ij, so like it's isotropic. And in this case we can also define bulk's modulus, and since we know from J this was a formula for bulk modulus which is equal to k is equals to bulk modulus is equal to Young's modulus upon 3 upon 1 minus 2v. And like we obviously know that if the bulk's modulus is infinite, then the fluid is incompressible. And the bulk's modulus is also defined as delta V upon V times delta P. It's basically the change in volume per unit pressure. So like this is basically these are the two cases for like with the stress strain relationships work out. And like basically these are the relationship between the Young's modulus and the lambda and mu parameters which we defined. So you can basically take any two of this, either you can take lambda or mu, or either you can take the Poisson's ratio and Young's modulus and material properties and basically substitute them to get a relationship between this sigma and epsilon. So yes, I guess that's it for this video. I'll see you in the next one.